Example 1.4.4b. Determine the RMS value of the voltage induced in a 30-turn coil by a spinning magnet if the cross-sectional area linked by the flux is 20 centimeters by 20 centimeters per loop, the peak flux density is 1.65 Tesla, and the magnet spins at 3,600 RPM. So we finally built up to the point where we can solve a problem that is very similar to how electricity is actually generated in real-world electrical generators. Most power plants have a magnet that spins inside of a coil. So this is just an application-specific solving of Faraday's law of induction. Our givens are that there are 30 turns of coil. There is a cross-sectional area of the coil where the linked flux area is 20 centimeters by 20 centimeters. The next is the peak flux density. You have to know that the symbol for flux density is capital B. I'm going to give that a subscript M for max or peak, whatever you prefer. There's no real guidelines there. Just indicate that you know that it's not a RMS value. We know that's 1.65 Tesla. A reminder that 1 Weber per meter squared is equivalent to a Tesla, which is the more modern unit of flux density. Webers per square meter being a little bit older. And then we need to know how fast this magnet is spinning. That's 3,600 RPM, which stands for rotations per minute. And we are asked to find what is the induced RMS voltage in the coil of wire by this spinning magnet. So in the chapter we derived an equation for the voltage, the sinusoidal voltage that is induced in a coil of wire by a magnet that spins inside of a circle. And that formula was that the induced EMF is the number of turns times the peak magnetic flux times the angular rate of rotation times the cosine of angular rate of rotation times time. And the product of N, phi max, and omega is the max voltage. So we multiply those three together and we get a peak voltage. So that's what we'll do. We'll solve for that peak voltage or the max voltage, and then we'll convert from peak to RMS. So our problem statement gave us peak flux density but not peak linked flux, so we need to solve for the linked flux. And we know that that's just going to be the product of the peak flux density times the linked area, which is 20 centimeters by 20 centimeters. And if you solve that, you'll get 0.66 Weber. Right. Remember that the Tesla is a Weber per square meter, and so centimeter times centimeter needs to be converted over to square meters for this calculation. Next, we need to know omega. We weren't given angular rate of rotation. We were given RPMs, which is 1 rotation per minute, or 3,600 rotations per minute. So we need to convert from RPM over into rads per second, radians per second. To do that, first I'm going to convert the minutes to seconds. So 1 minute is 60 seconds. And then you have to know that a full rotation is 2 pi radians. So just remember there are 2 pi radians in a circle. You learned that a long time ago. So there we go, 2 pi radians per rotation. Multiply all of that out and you are going to get 120 pi radians. It's pretty common we don't multiply through by pi so that we get more exact answers using our calculator. So if I want to calculate the peak voltage induced by this rotating magnet, I just need to multiply my linked flux, which was 0.66 Webers, times the number of turns of coil, which was 30, times the angular rate of rotation, which was 120 pi. And that gives me a peak voltage induced of 746.44 volts. We should throw a negative sign on there, but remember this is a sinusoid, so that doesn't really mean anything. It's just a phase indication. Now we need to convert from peak to RMS, and we do that by either dividing by square root of 2 or multiplying by 0.707. You get 528 volts as the peak induced voltage for this particular generator.